Okay, good morning. So my name is Ning Lu from Thompson Rivers University, a small university in British Columbia, Canada. So this is a joint work with Bo Ji from Temple University and Bin from University of Rhode Island. So I will start right from the beginning. We are now facing a cyber-physical world, and everything will be interconnected. For example, in the domain of Internet of Things, we have smart grid, smart factory, and smart homes. Okay, so in the center of the technology, that's a cyber-physical system, a tight integration of computing, computation, and decision making, providing support for all this exciting stuff. So we have seen recently the deployment of many real-time applications. For example, what we have here is a real-time monitoring smart factory, and what's happening here is multiple sensors measure variables of a plant, and all the measurements are required to send to the central controller through, for example, a wireless network for control and monitoring purposes. And to keep the usefulness of the measurement, we have to send the measurement in a timely manner. Otherwise, it will become stale and thus useless. And too many useless measurements might not be tolerable and could affect the stability and control performance of the system. Okay? And so there are two key messages from the real-time applications. First, they require a timely information delivery, and secondly, violating the time limitation beyond certain thresholds is not acceptable. Okay? And real-time scheduling problems aim at scheduling deadline constraint packets to guarantee a minimum portion of packets to be delivered on time. So what we have here is, it just show one link here, but we have a bunch of links, and each packet is associated with a deadline. Okay, so we impose a hard deadline on each packet reception, and drop packets not delivered by deadline. And the goal is to guarantee a minimum portion of packets to be delivered on time. Okay, we call it timely throughput. Okay, so it is worth noting that imposing a hard deadline on each packet's reception basically guarantees that the received packet at the time of reception is fresh or useful, and guarantee the timely throughput assures that the destination receives timely throughput at a desired rate. Okay, but that might not be sufficient to guarantee the information freshness in the real-time system. For example, the same example, and this sensor right here keeps sending measurement of inventory to a central controller here. And the most recent measurement of the inventory could become out of date to the controller if the controller waits too long before the next update. Okay, so which can lead to the disturbance in the monitoring system, the monitoring and control. Okay, so the measurements are expected to send to the central controller or update at the central controller regularly or timely. So this means maintaining the data freshness at the receiver side is also crucial. Okay? So I will keep this short because recently the age of information is proposed as a metric of information freshness at the destination. Okay? So by definition, age of the information is the age of the youngest data sample delivered to the receiver, okay, before time t. For example, at time t, the age of the information is that much, which is the age of the sample, the most recent sample generated here and delivered by them. Okay? So, motivated by the AOI, the age of information in research, and the importance of maintaining data freshness at the receiver side. So we are particularly interested in design real-time scheduling algorithm, considering providing both the timely throughput guarantee and as well as improving the data freshness at the receiver side. Okay, so yeah, we want to assure that the destination receives timely packets at the desired rate, as well as improve the data freshness in terms of AUI at the receiver side. Okay, so that's the goal of this work. So let's take a look at the system model. So the real-time scheduling problem is formulated this way. What's going on here is we have a network of a bunch of single hop links, and each link has a sender and a receiver. The packets arrive at the sender queue is associated with a deadline, okay? And the packet has to be delivered before the deadline, otherwise the packet will be dropped, okay? So for each link, for every link L, the arrival rate is lambda L, and it is required the fractional packet loss due to deadline expiry has to be less than or equal to some percentage gamma L, okay? For example, gamma L could be 0.2. That means at least we can maximum drop 20% packet. Okay, so this is equivalent to a timely throughput requirement. Okay, we have to deliver at least lambda L times 1 minus gamma L traffic on time. Okay. So, but the real-time scheduling problem under general interference model, traffic arrival model, and channel and deadline models could be very difficult. Okay? So a modest goal is to tackle this problem under a simplified frame-based model. So what's happening here is that we consider a various system having L links, okay? And they share one communication channel, and channel access time is in frames. Okay? So the packet arrivals only occur at the beginning of each frame, and the packet has to be delivered at the end of the frame, otherwise it will be dropped. Okay. So this implies all the packets have the same deadline T. Okay? Same deadline T. So let's see what will be AOI look like under the frame-based model. So this is the AOI. Okay, so basically the AOI of a link L at frame K, okay, denoted by RLK, is the number of frames lapsed up to frame K. Okay, since the most recent successful packet delivery on link L. Okay, and as you can see up there, the AOI is updated at the beginning of every frame and grows linearly until a link L has one packet successfully delivered and then drop to 1, which is the age of the most recent update. Okay, so and now we provide an example here show how to improve the data freshness by appropriately scheduling traffic, okay, packet delivery. So up there, if we only consider this period of time, 11 frames, so the deliver of packet A, B, and E lead to the decrease of AOI, okay, AOI. And this basically a 60% packet delivery rates out of 5 arrivals. Okay, so we have an average delivery ratio of 60%, but if you compute the average AOI, that's 2.27 frames. Okay, so down here, and we have exactly the same arrival pattern. Okay, and but the difference is we deliver packet D instead of E. Okay, so and this leads to the same packet delivery ratio, but improved AOI to 2 frames. Okay, so this is how to example of change the scheduling decision to improve the AOI. Okay, so under the frame model, the scheduled transmissions in each frame looks like this. So basically, we have a number of slots and we have a number of links. Okay, so in each slot, we set a bunch of links to on state or one state, and other links to off states. Okay, off state. So in on state means the packet is allowed to the link is allowed to transmit packets during that time slot, and otherwise the link has to keep silent. So the set of unlinks has to satisfy the interference constraint. That means any two links from that set won't interfere with each other. Okay. So and we consider a known channel state information CLK. That is the number of packets can be sent at each time slot in frame K. And one more time slot can be scheduled to link for packet transmission. For example, for link 1, there are 3 ones. That means 3 time slots allocated to that link for packet transmission. Okay, could be more than 1. Okay, and so the schedule of the transmission over a frame looks like a matrix of 1 and zeros. Okay, so the problem of real-time scheduling is to find the schedule, the best schedule in every frame to meet our goal. So the first technique introduced to do the real-time scheduling design is the introduction of virtual queue. Basically, this the VLK, that's the length of this virtual queue, which is to track the dropped packet, the number of dropped packet. So what's going on here is that each link maintains a virtual queue, and the arrivals, that's the arrival, like tokens, for example, that's the number of dropped packet in each frame, and the departures at a rate of lambda L times gamma L in each frame. So lambda L times gamma L, that's the maximum allowable dropping rate. So what's happening here is we have the actual dropping rate, and that's the maximum we can drop. Okay. So if anything positive within the queue, that means a deficit, okay, in the required timely throughput. So we keep track of the deficit, and the intuition is if a link with a larger virtual queue length has to be scheduled more often, okay, to reduce its queue length. So this brings us the traditional MaxWeight real-time scheduling. So it schedules, it picks a schedule with maximum weight in each frame. So this is how we define the weight. So we have a virtual queue length, okay, and times the minimum of this and this. Okay, so the first item is basically the potential service. Okay, so CLK, that's the number of packets can be sent in each time slot, and times by the number of ones, okay, number of time slots allocated to that link L, under a particular schedule. Okay, and arrivals. Okay, and this basically gives us the actual service. Okay, and then weighted by the virtual queue length, we get a weight of a link. Okay, and if we do the summation over all links, we get a weight of a schedule. Okay, so max weight just pick up the one with the max weight. Okay, so so the intuition behind this is we want to serve links with the largest weight as much as possible. Okay? And this is optimal in the sense of stabilizing all virtual queues. However, this is we don't have here the max weight doesn't consider the improvement of data freshness. Okay, so let's take a look at our solution. So that is AOI-based real-time scheduling in each time slot in each frame K, and this is a traditional max weight. Okay, and we introduce the AOI of each link. And now we, the actual service is weighted by a linear combination of the virtual queue length and the age of the link. Okay, so zeta and beta here are just control parameters. Okay. So if you look at our policy, and when zeta takes 0, for example, and our policy becomes the virtual queue length based policy, so the traditional max weight policy. And we will show that it cannot provide a data freshness guarantee. Okay? And when zeta takes 1, basically it becomes the AOI greedy policy where we just minimize the AOI without considering the virtual queue length. Okay, So we will show that our policy provides both timely throughput guarantee as well as data freshness guarantee. Okay. So we have some analytical results. So first, we prove that the AOI-RT policy is feasibility optimal. So that means the policy can stabilize all virtual queues. Okay. So this is done by using drift analysis, considering the optimal function like this, okay, like this. And the key observation is that the expected total virtual queue length, okay, increases exponentially with the increase of zeta, okay, and it becomes unbounded when zeta equal to 1. Okay, so when zeta equal to 1 corresponds to the AOI greedy policy, so that means the AOI greedy policy is not capable of guaranteeing timely throughput. Okay. And we then derive an upper bound on defined network data freshness. Okay. So the network data freshness is defined like that. Okay. So that is a summation over all links of weighted expected AOI. Okay. So the bar means just AOI in steady state. Okay, so this is upper bounded by some constant plus 1 over zeta minus 1 times some constant. Okay, so gamma omega L, there's just a preference of the length towards the data freshness. Okay, so this is the proof is done by considering another layout function. So as you can see up there, the observation is that the network data freshness improves with the increase of zeta, okay, and it becomes the unbounded when zeta takes 0. Okay, and zeta takes 0 corresponds to the MaxWeight, traditional MaxWeight of virtual queue length based policy. So that means the virtual queue based policy cannot provide data freshness guarantee. Okay, and then we derive the convergence of timely throughput under the AOI-RT policy, so which looks like this. Okay, so the deviation between the running average of timely throughput minus the some long-term throughput, so which is at least lambda L times 1 minus gamma L. Okay, and the summation over all links, okay, upper bounded by some constant plus 1 over k times the expected total virtual queue length. Okay, so this the upper bound is dependent on the total expected virtual queue length. And so the key observation is that the increase of the expected virtual queue length slows down the convergence of the timely throughput. Okay, and this becomes unbounded, the expected total virtual queue length when zeta takes 1. Okay, zeta takes 1. So data takes 1 corresponds to the AOI greedy policy. Okay. And now we review the throughput, the trade-off between data freshness and the convergence of timely throughput. Sure. So here, that's a control parameter of our policy. When zeta takes 0, no data freshness guarantee. Okay. That's a virtual queue-based policy. And when zeta takes 1, that's the AOI greedy policy and no timely throughput guarantee. And anything between that can provide both guarantees. Okay, and if we increase zeta, basically we improve the data freshness at the cost of slowing down the convergence of timely throughput. Okay, and we do some simulations. So to validate our analytic result, we did 2 sets of simulation. First, we did a simulation on a network of 100 links. Okay, in a fully connected network in the same interference region. So, and we show the improvement of network data freshness with respect to zeta. Okay, so we consider some links having heavier traffic and some links have lighter traffic, and the rho there is just a parameter to control the size of the 2 groups. Okay. And yeah, as you can see, with the increase of zeta, we have an improvement of data freshness. And that is the relative change of the timely throughput compared to the requirement. As you can see, when zeta takes 1, we cannot guarantee the timely throughput. Okay? So there is no guarantee. And the last one, the right corner gives you the data freshness versus the virtual queue length. Okay? The total expected virtual queue length. Okay? With the increase of zeta, we see we have an improvement in terms of network data freshness, but the total average virtual queue length goes large and slows down the timely throughput convergence. And we also did a simulation in a 10-link ad-hoc network. And so to investigate the per link AOI performance, this is a histogram of AOI, per link AOI. And with zeta takes 0 and takes some value close to 1, as you can see, the occurrence of a large AOI becomes less often with zeta takes something close to 1. Okay? So that means the improved AOI per link AOI performance is improved, and this can also be demonstrated by showing a CCDF of the per link AOI. Okay? And the last one shows the convergence, the timely throughput deviation with respect to the different values of zeta, okay, with zeta. So as you can see, if zeta goes large, basically it slows down the convergence. Okay. So, so again, to conclude, we have proposed AOI-RT policy for scheduling real-time traffic to provide both guarantees on timely throughput and data freshness. Okay. And in terms of policy, algorithms takes the virtual queue length and the AOI of each link as driving factors in making scheduling decisions. Okay. And we also investigate the trade-off between data freshness and the convergence of timely throughput. Okay. So future works, for example, include the distributed implementation of this policy, because this is centralized, requires queue length information and AOI information of each link. So, any questions?